The inclined plane. We can now solve problems with gravitational potential energy, kinetic energy, and elastic potential energy in 2 dimensions. Energy is a scalar, but its value depends on an object's motion components along the x and y axis. Let's look at the gravitational potential energy first. If an object is moving along an incline, and let's just draw that here, does its potential energy directly depend on the distance traveled along the incline? And we list here, this is your conservation of total mechanical energy, where you have your initial gravitational potential energy, Ke, and initial elastic energy equal to the final, as there's no external work being done. So the question is, what does this term depend on? This distance here directly? Let's move on. So let's set the question up a little bit more. You push this box over here, up the incline, a distance d, to a height h above the ground. The calculation of the potential energy will depend on what is given for the problem. They will either give you d or h. And we're going to make an assumption that the gravitational potential energy at the bottom here is 0. And of course we're free to set that point anywhere we'd like. This time the logical place is at the bottom of the incline. Now to answer our question. The gravitational force always points down. Now work only includes the distance and force components that are in parallel, because the potential energy is equal to the negative of the work done by the gravitational field. That directly involves this term right here. H is in the same direction as the gravitational force. D is not. However, if we take the projection of D on H, well, that's d sine theta. H is equal to d sine theta. That would work. So your potential energy directly depends on H and kind of indirectly on D. You have to multiply it by sine theta. Again, just to drive the point home, kinetic energy is a scalar. However, it's equal to 1/2 mv squared, so it's relating directly to the velocity, and velocity is a vector. So when we perform calculations of velocity from kinetic energy and relate it to the gravitational potential energy, we need to be careful to relate the change in the gravitational potential energy only to the change of kinetic energy in the y direction, this direction right here. So what we're saying is if an object's moving like this with a certain amount of kinetic energy, and a velocity of course, all we count is the velocity in this direction when we try and relate it to potential energy. Okay, how about elastic potential energy now? In the case of elastic potential energy, the amount that the spring is compressed is the important variable. No trigonometry is required. So now kinetic energy will either use the vertical displacement that an object covers, that's in the up and down direction when we want to relate it to the gravitational potential energy, or the actual displacement of the object from the spring's force when we relate it to elastic potential energy. So if a spring is compressed in this direction, this is our delta x for the spring. If it's up like this, this is delta x. We just align it with the spring.